Okay, everyone, welcome back to class. Good morning. It is August 29th here, so we're finishing up our second week of the semester. We're hopefully going to finish off chapter 2 today. If we don't finish all of it today, we'll finish it up quickly on Tuesday, and we'll have at least some time for review on Tuesday. Later today or early tomorrow, I will post some review materials for you guys. So I've got a recording that I did for an online class, uh, so you can watch that review session, and then I have a packet of review problems as well that I'll post on Canvas later today or early tomorrow for you guys. Okay, so the first exam will open on Wednesday, and it'll be open for 3 days. So you can take it anytime during those 3 days at a testing center. Next Thursday, we won't meet. I'll leave that slot open for taking the exam. So we won't meet in class. Okay. And the reason why is because at least some of you guys are going to be busy during those 3 days, right? And this class time might be the only time you can get down to the testing center. So I'll leave that Thursday open for you to get down to the testing center if you need it. Are there any questions that you guys have that you want to go over before we jump into the last part of chapter 2 and finish off that? Nothing? Okay. Well, let's get going then. So we left off with this quirky paper, this research journal article, and they were investigating this thing called behavioral asymmetry. Okay, so it's a fascinating topic. Where are the testing centers at? Oh, okay. So let's just go back here to the modules, and I want to show you all the information you need for scheduling your exam. So in the orientation, there's a page that says online, testing center information right here. Okay, so this should be somewhere on Canvas. If you can't find it, let me know. And they have all the information here. So if you live in the Salt Lake area, you'll want to go to this testing center reservation link. If you live outside of the area, then you'll have to do a remote proctor. It's a little more work, but once you get it set up, it's not that bad. Okay, so there are at least 3 testing centers that I'm aware of. There's one at the South City campus, which is closer to downtown. There's one at the Redwood campus in the library, in the basement of the library. And then I'm pretty sure there's one at Jordan as well. And there might be another one. I'm just not really sure myself. Okay, so to schedule the exam, you'll come in here. It'll take you to your My SLCC. You'll log in and just follow these directions. There should be a testing services tile card. And then let's see if we can find that. Where are the tile cards? Let's see here. So you log in. Let's see if it'll let me do this quickly. Okay, and then, oh yeah, testing services right here. So, okay, so it looks like there's one at the Harriman campus as well. Since you guys this is a Zoom class, you can take it at any of these campuses. So you'll click in there. Your screen will look different than mine, right? Because I'm not taking the course, right? So anyway, it's in here. The direction, the directions are on the website. And then let's see, I've got another question here. I know you can bring an 8.5 by 11 paper. Yes, you can fill it out on both sides. Okay, so just your typical printer paper or smaller, and you can write on both sides of it anything you want, pictures, example problems. You can type it, you can write it in your own coded language, whatever you want. Anything you want on there, you can have on that paper both sides. Okay. Any other questions? All right. So let's go ahead and finish off chapter 2 then. And so yeah, it was this thing called behavioral asymmetry, and it's like, well, there's more people who are right-handed than left-handed. I think it's about 85 8 to 88% of people are right-handed, and then you've got about 12 to 15% that are left-handed. But it turns out that is also the case for footedness, and people apparently even have like preferred eyes that they use. And so there's this asymmetry in behavior. Okay, the body, is basically symmetrical, right? But as far as behavior goes, there's an asymmetry there. And so what this guy was doing is he knew from his studies that and from the literature that fetuses, okay, so babies during pregnancy have a tendency to turn their head to the right more than the left. It's established. That's not what this paper was about. He knew that, and he thought, well, maybe this behavior would persist into adulthood. And so what he did is he went out and he observed 124 couples kissing, right? So it's a little bit funny the way it sounds, but and then he noticed that a pretty good majority of them were turning to the right. Okay, so it's about 65% were turning to the right. Yeah, and so we use this to set up the hypotheses. So this is the hypothesis test, and we'll be doing these all semester. And as long as you study or use statistics, you'll probably be doing these hypothesis tests. They're very commonly used. So the null is that there's no preference for right or left. Okay, and that would be if the proportion of right turns was 50%. And so here we're talking about at the population level. So all head turning, which of course we can't measure directly, right? So that would be no preference. And then if there's a preference for right turns, then P at the population level, the population proportion would be more than 50%. Now we're not saying that it's 100%. We're not saying that people never turn to the left. We're just saying that there's some preference for turning to the right. So as long as P is more than 50, there is a preference. Okay, now if P is 51, it's not really a strong preference. If P is 80, then it's a strong preference, something like that, right? So we're not trying to establish what P is. We're just trying to see if it's more than 50. Okay, and then so we notice that 65% is about 15% more than 50%. And I asked you guys if that's strong evidence. Okay, do you think that's weak evidence? Do you think it's extremely strong evidence? Or is it somewhat convincing? And I think most of you guys said it was somewhat convincing, but you weren't really super convinced, right? And so what we decided to do is we were going to find something in nature or in the world that acts like a 50-50 process. So with the hypothesis test, we're going to assume that the null is true. So we're going to say, okay, if we have a 50-50 event that happens 124 times, how likely is it that we would get 80 of that event, right? Okay, so again, we have a 50-50 process with two outcomes. We're going to do that event 124 times, and we're going to say how likely is it that we would get 80 or more out of 124. So we're going to flip a coin, right? Because coins, we assume that they're 50-50. And so when we get started with this idea, it's nice to be really kind of hands-on and, concrete with this. So I'm going to have you guys flip coins, okay? Now, if you have a physical coin, that's great. But if you're like me, you don't typically have a coin, sitting around. So here's what we're going to do. There are 14 students in here. Okay, so there's 14 of you guys that I'm seeing. So we've got 14. How many flips do we need? We need 124 flips because that's how many were in the study, right? There were 124 couples that he looked at. Must have been kind of weird and awkward when he did that, but who knows? Maybe he was maybe that's fun, right? Who knows? So 124 divided by 14, we have 8.9. So I need 8.9 flips from everybody. So if everybody did 9, we'd have too many. So let's round that down. I need everybody to flip a coin 8 times. But before you do that, let me tell you exactly how I want it done. Otherwise, this can get really weird and messed up. So you need to either have a physical coin or actually, let's see. We have 15, don't we? I'll go ahead and participate as well. So let's see here. So we have 15. Oh, there's a 16th person. Okay, there's 16 people in here now. So we're going to go 124 divided by 16. And so, if everybody did 8 flips, we'd have too many. So 7 flips from everybody. So let me show you exactly how this is going to work. Okay, so pay very close attention here because we don't want to mess this up. Okay, so we need 7 flips from everybody. So I need you to go to this website called, it's on Google. It's this coin flipper. Or if you have your own favorite random coin flipper, you can use that. But my guess is you don't do this too regularly outside of class. So go ahead and go to this website and watch what I'm about to do. I'm going to flip a coin 7 times, okay? So here we go. I'm going to flip a coin, and I'm going to say, okay, I got heads. Okay, then I'm going to flip the coin again. Heads. Flip the coin again. Tails. 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 Here's my 7th flip. Tails. Okay, so I'm not interested in, the order in which you got it. I'm just interested in the total number of heads that you got. Okay, so mine is 2. Okay, so I had 2 heads. All right, and so all I want is one number, right? A single digit in the chat. Okay, and that digit is the number of heads you get. Okay, so Polly got 3 heads. Okay, and so you get the idea? Okay, great. So yeah, just put your numbers over there. And again, I just want one digit, and that's the number of heads. I don't care, you don't need to tell me anything else about the order. I just need to know how many heads you got. Okay. And so it is important that everybody participates here because we don't, we need to generate a bunch of flips. Yeah. So I'll give you guys a few minutes to let those numbers roll in here. And if you're unsure about what to do, just let me know. I can explain it again. And please don't make up numbers. So if you're unclear what to do, don't just make up a number. It might be tempting, but okay, so how many is that? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 people. Okay, was there a 16th person who was going to participate? Maybe I miscounted. Okay, if there's nobody else, then let's go ahead and see where we're at. Okay, so we have 15 people, right, who have participated. So you guys all flipped it 7 times, right? So how many flips do we have? We have 15 times 7 flips. We have a total of 105 flips. Okay, so $105 flips. Does that sound right? Let's see, 1, 2, 3, 4, 6. Okay. So what are we gonna do? We're a little bit short. How short are we? Well, we need 124. We're at 105. So we need 19 more flips, right? So 125 minus 124 minus 105, we need 19 more flips. Okay, so here's what I'm going to do. I'm going to go to a random number generator and I'm going to do this 19 times, but I don't want to flip the coin 19 times by itself. So I'm going to come over here to my other random number generator and I'm going to say, well, I need to do this 19 times. Okay, so basically I'm just doing this quickly. And so it's just going to save us some time. So does that make sense? So I'm not cheating or doing anything weird here. I'm just doing 19 flips to make up the rest. Okay, so it's just another random number generator, another coin flipper, and I asked it, okay, I want 19 flips, and it did 9 heads. So we're gonna have 9 more here. Okay, and then so these numbers here are the total number of heads we got out of our 124 flips. Okay, so everybody do this along with me so I don't mess this up. I'm going to add up all these numbers, and then this will tell us how many heads we got, right? Okay, so 2 plus 3 plus 5 plus 3 plus 8. I'm seeing 62 here. What did the rest of you guys get? So we got 62 heads out of 124 flips. I believe so. Okay, great. Thank you, Julia, for confirming. So what is that? That's our simulated p hat. Okay, so we had 62 heads out of 124 flips. And why are we doing this? We're trying to get an idea of how weird it is or how unusual it is, if it's weird at all, of getting 65% of a 50-50 process being right turns. Okay, so what is that? What's the result here? So we have 62 divided by 124. So we're going to go 62 divided by 124. And of course, we're expecting something close to 50%. And it's almost too perfect. It's exactly 50%, which is kind of weird, right? I mean, we'd expect it to be a little bit away from 50% just because of the way randomness works. But what that's saying is okay, let's see, what we would expect to have happen if we had a 50-50 process and we did 124 times. So how far from 50 are we? Well, we're not far at all. We're right at 50, right? So the idea is that should give us another data point for understanding how unusual 65% is. What do you guys think? Do our results make this more unusual or less unusual? Are you more convinced or are you less convinced after flipping that coin? Or are you totally confused and you have no idea, what the coin flipping is all about? What do you guys think? Are you more convinced or less convinced? You're more convinced, yeah. And why is that? Because what we just saw is that in a 50-50 process, if you do it 124 times, at least the one time we did it ourselves, it didn't really fall very far from 50%. In fact, it fell right at 50%. So their result is 15% away from 50%. So you're probably a little bit more convinced. Maybe you're not totally convinced. Some of you might be totally convinced at this point. But that's great. Okay. And then so now what are we going to do? Well, now we're basically going to flip that coin a bunch of times using software to help us get a better feel for how unlikely this is. Okay. So what we're going to do is we're going to go to this applet that we have, and we're going to flip 124 coins very quickly using the applet. And then I think we'll see why this paper was so convincing to so many people. Okay, what we're going to find is that 65% is very, very convincing. Okay, so let's go over to our applet and do this in a different way. Okay, so let me show you this applet. This is an important applet for you to get comfortable with because it's actually going to show up on exams and on the project. Okay, so it's here in the lecture notes. So if you have your lecture notes open, you can click on this link here. So it's the Rossmann Chance website, and they have all of these great applets that help you understand and investigate probability. Okay, so just click on that. And if you have a hard time clicking on that, then I'll put a similar link. It's actually to the same website. The link looks a little bit different, but it's the same website. So you can click on this link in the chat. And I want you to come over here to this applet. Okay, so when you click on that, it'll take you to something that looks like this, and it says one proportion. And then I'm going to come over here and I'm going to say, all right, we have a 50-50 process, right? And I'm going to start flipping coins here. Okay. So I'm not going to flip one coin. I'm going to flip it 124 times, right? So by going 124 here, it does what we just did as a class. It took us like, what, 10 minutes to 15 minutes to do that. It'll do this in a millisecond or even less, okay? So by hitting the 124 here, let's turn off the animation. It will flip 124 coins. Ready? So I'm going to hit the draw samples here, and immediately it gives us 124 flips of a coin. How many heads did we get? We got 54. Okay, so it's a little bit less than we would have expected maybe. Okay, but that's good. It's giving us an idea of kind of the fluctuations in p hat, right? So if there's no preference for right or left, this is giving us an idea of kind of how much fluctuation we would expect in p hat. So let's do that again. Okay, and again and again and again and again. We just keep doing it over and over and over again. And what is it that we're interested in? We're interested in seeing how often we get something that's 80 or more. Remember, 80 is what that researcher got, right? He had 80. So I'm going to come down here to where it says as extreme as, and I'm going to put in 80. And what that does is it sets up a boundary for us, like a barrier. And any result that's past that barrier or boundary is as extreme as what he got in his paper. Okay, so anytime we get a dot that goes out that far, that's evidence saying that his results aren't that unusual. Okay, dots that don't go out that far are evidence that his results are unusual, right? So let's keep doing this. Okay, so we just keep pressing this, and it's kind of fun. I mean, if you're mathematically minded, it's kind of interesting to think about this, but before long we get kind of bored with this. By the way, I think you do start to see a pattern here. It looks like most of the random simulations are pretty close to about 62, which is about 50-50, right? And then as we get further away from 50%, they start to decline, right? So if you've studied stats before, you might have heard of the bell-shaped distribution. This is basically the beginnings of a bell-shaped distribution. Okay, and then so the other thing we can do is instead of the number of heads, we can look at the proportion of heads. Okay, so 50% is here in the middle. So we're getting most of the simulations there, and then his result was about 65%. Okay, so how many times have we done this? We've done 100 rounds of 124. Okay, so in our class we flipped a coin 124 times. Now with the help of software, we've done 100 rounds of what we did in class together. Okay, so it speeds things up quite a bit. And we can speed it up even more by increasing the number of rounds each time. Okay, so, but so far, how many times have we gotten something as extreme as his result? Well, none, right? So we've done this 100 times, and not a single case was as extreme as what he got. Okay, so we're starting to get pretty good evidence that his results are very strong, right? That they're what we call statistically significant. So let's do this maybe 100 times. Okay, so when I do 100 here, it's going to do 100 rounds of 124 flips. Okay, so it's flipping a ton of coins very quickly. And so when I hit the draw samples, it's going to create 100 more dots for us. And the picture really does start to look like a bell-shaped curve after a while. Okay, so we're at 700 rounds of 124 flips. Okay, so we've basically done 1,000 rounds now of 124 flips. So take what we did in our class. It took us like 15 minutes to do that. We've done that now 1,000 times with this software. Okay, and so we start to get that bell-shaped curve here. And those 1,000 random simulations, how many times did we get something that was more than 65%? I'd like somebody to comment on that. How many times did out of 1,000 we had 0? Yeah, exactly. Okay, so that should be very strong evidence in your mind that his results are significant, right? That there is a preference for turning to the right. Okay, now we're not trying to say how strong the preference is. We're just trying to say how strong the evidence is that there is some preference. Okay, so clearly people still turn their head to the left, right? Like 45% of the couples were turning to the left, so still pretty common. But there is a preference for the right, is what this is saying. Okay, so let's do this a couple more times. If you read the book, the example in the book, they do the same thing with the software, and they run the simulation 1,000 times. I think they had about 6 times out of 1,000. So let's do this maybe. Let's go up to 2,000 here, and look at that. We're at 2,000 rounds, and we still haven't had a single one as extreme as what they got in their paper. Okay, so let me just keep going here because eventually it does happen by chance. We're at 3,000 rounds now. We haven't had a single one as extreme. There we go. Wow, I've never had it take that long. We had to do this 4,000 rounds of 124 before we got something as extreme as what he got in his paper. Okay, so by the time you get to your 4,000th trial run here, your 4,000th round of 124, we do get something by chance that's as extreme as what he got. Okay, so it can happen, but it's very, very unlikely. Okay, so do you see that 1 out of 4,000? This value is called the p-value. Okay, and I mentioned that word last time. This 1 in 4,000 that we just got is called the p-value. Okay, so 1 out of 4,000 point. Yeah, so that's a good question, Noah. So yeah, we have 4,000 rounds of 124. So we did flip the coin. Let's see, yeah. So let's see, yeah. I think you're exactly right. If we go 124 times 4,000, there were almost 500,000 coin flips. But it's not that we got 1 out of 500,000 because each of those 120, so you have to break them up into groups of 124 flips, right? Because one round of 124 is equivalent to his experiment that he did. Does that make sense? So it truly is 1 out of 4,000 rounds that we got something as extreme as what he got. Good. So does that make sense? It does take a little bit to wrap the mind around it, but so what's that p-value? We have 0.0003. Okay, so this is called the p-value, and we have strong evidence that there's a preference for turning to the right. Okay, so we would not expect this if the null were true. Okay, remember what the null is. The null is no preference. Okay, so if there's no preference, we wouldn't expect to just see it 1 out of 4,000 times, right? So we would not expect this if the null were true. So what's our conclusion? The null is false. The null is false. We reject the null and we accept the alternative. So we say we accept the alternative hypothesis, which is that there is a preference for right turns. Okay, so we're not saying that it's, that people never turn to the left. We're just saying that, statistically there is at least some, it's just at least somewhat more common for turning to the right. Okay, great. All right, so that's a super important step that we've taken here. We've introduced the idea of the hypothesis test. We've looked at our applet. This applet's going to be all over the place here this semester for us. Now that we've got the idea of a hypothesis test, kind of an initial introduction to it, we're going to take a deeper dive into the various aspects of the hypothesis test, because I'll be honest, it's fairly complicated, and there's lots of pieces to it. So So what we do here is we take the hypothesis test and we're going to slice it down into its steps, and we're going to investigate each of those steps more closely. Okay, so we're going to, instead of looking at whole studies like we just did, we're going to look at just small micro portions of the hypothesis test until we understand all of those pieces of the hypothesis test. Then we'll bring them all back together and do another formal study. Okay, yeah, let's think about various parts of the hypothesis test. So as I was saying, the p-value, that's the probability of observing a sample data, right, at least as favorable to the alternative hypothesis as our current data set if the null hypothesis were true. Okay, so when you're doing a hypothesis test, you're always assuming that the null is true. So you're saying, okay, if the null is true, if the established wisdom is true, then how likely is it that we would get our sample that we got? Okay, all right, so the test statistic, that's a summary statistic of the data that's used to compare the p-value, to compute the p-value and to evaluate the hypotheses. Okay, if the p-value is small, like what we got earlier, we say that the results are statistically significant. Okay, so how small is small? Okay, so we got 0.0003. That just sort of seems like it's a small p-value, but what if we got 0.03? What if we got 0.3? Are those small values? Well, it depends on what your threshold is. Okay, and every field, if you work in biostatistics, they'll have kind of their threshold, their common threshold. If you work in physics, they've got their own common threshold. If you work in economics, they have their own threshold. Okay, so the threshold kind of depends on what field you work in. And so we want that to be a little bit flexible, right, from field to field. So we call that threshold the significance level. Okay, so the significance level is the threshold we use for determining if the p-value is small enough so that we can say we have statistically significant results. Okay. It'll all come into focus if it's not yet. Okay. We're going to be doing this all semester. So you've got you'll have lots of times that you can, you'll have a lot of experience with this by the end of the semester. Okay. So significance level, it's not, those aren't the biggest and longest words out there, but we get kind of tired of writing that out. So we have a Greek letter that we use to stand for the significance level. It's called alpha. Okay, so this is the Greek letter alpha. Okay, and it is the same as the significance level. So what we do is we have our hypotheses, then we go out and we generate simulated data using the applet. Then that will tell us the p-value, and then we compare the p-value to the significance level. Okay, so a common level for alpha is 0.05, but that's not the only one that's used. Okay, historically, so the hypothesis test, the statistical hypothesis test, was developed in the 20th century, and so if you look at the history of that, they commonly were using 0.05 for alpha. So that's just kind of the typical alpha value that we'll have. But sometimes it'll be a little bit larger, sometimes a little bit smaller. So let's take a deeper dive into that slice of the hypothesis test where we take our p-value that we get from our applet and we compare it to alpha, the significance level. Okay, so the idea is this. If, and you'll want to write this down, put it on your formula card, if the p-value is less than alpha, then the results are statistically significant. And let me just write one other thing. We're going to reject the null. Okay. If the p-value is more than alpha, then it's not statistically significant, and we do not reject the null. Okay. We just simply don't have enough evidence to overturn kind of the established wisdom. Okay. And that's fine. I mean, if the established wisdom is true, we don't want to throw it out, right? Okay, good. So alpha equals 0.05, p-value 0.124, then in that case, the inequality goes towards the p-value, which means it's not statistically significant. You guys try the other three. Okay, so again, we're not looking at entire studies here. We're just focused on one small part of the hypothesis test, and we're just practicing with this step where you take p-value and you compare it to alpha. Okay, so you guys do these other three, and somebody in the chat just tell me yes, no, no, yes, whatever you think the right answer is here. So we have 4 scenarios. Okay. All right. So Brock is saying no on number 2. Does anybody have a differing opinion on that? What is this E doing here? You guys know what that is? That's called scientific notation. And what that tells us is the -4 tells us this is a really small number. And what that's saying is it's you have to move the decimal 4 places to the left. Okay, 1, 2, 3, 4. So really, this p-value here is 0.000235512. Okay, and that is actually less than 0.05. So this is actually a yes. Okay, so if the p-value is less than alpha, then the results are statistically significant and we reject the null. If the p-value is more than alpha, then they're not statistically significant and we don't reject the null. Okay, all right, then Lindsay is saying yes on number 3. I agree with you on that because 0.06 is less than alpha. So that would be statistically significant. And then Noah is saying no on number 4. And I agree with you on that because the p-value here is more than alpha. Okay, so that step occurs towards the end of this process after we've simulated our results, and we use the simulation to see how unlikely the actual sample results are if the null is true, right? Good. So what other things do we have to think about? What other steps are there in the hypothesis test? Well, we have to think about how things can go wrong, right? So when you're learning a new thing, right, and you want to do it well, it's very common to learn common pitfalls, right? And we've done that with sampling, for example, right? We talked about bad samples, not because we want to do them, but because we want to avoid them. We talked about bias, not because we want bias, but because we want to avoid it. So that's what we're going to do here. We're going to think about possible outcomes from a hypothesis test. Okay, and so there's a table here. Let's go ahead and fill this in, and then I'm going to give you a couple of what I consider to be nice examples for understanding this table. Okay, so when you do a hypothesis test, you're going to make a conclusion. Okay, either the results are significant and you reject the null, right? So if the results are statistically significant, you're going to reject the null. If they're not statistically significant, then you don't reject the null. Okay, but because your conclusion is based on a sample and not the entire population, there's always some possibility you can make the wrong decision. Have you ever made a wrong decision in life before? Okay, maybe you thought that this decision would be best, but later you find out you were wrong, or you just made the wrong decision. Yeah, I mean, it happens to us all, right? And so this does happen sometimes with hypothesis testing. So just because the conclusion is reject or not reject, that's not always the same as what's actually true in reality, right? So that guy, that researcher on the behavioral asymmetry, he was making a conclusion based on 124 people. Okay, but there's billions of people in the world, right? And so there is some truth about all people, right? There may be an asymmetry, there may not be, right, when it comes to head turning. And so in reality, either the null is true or the alternative is true. Okay, and since we sometimes make wrong decisions, it creates this mismatch, and there's 4 places where we could end up. Okay, if we fail to reject the null and the null is true, then we have made the correct decision. Okay, if we fail to reject the null, but the alternative is true, we've made a mistake, right? The alternative is true, but we didn't reject the false hypothesis, right? Okay, if we reject the null, but the null is true, then that's also an error, right? We basically threw out the established wisdom, but the established wisdom was actually correct, right? Okay, so that's an error. And then finally, if we reject the null and the alternative is true, then the test worked. So we've made a correct decision. Okay, so the correct decisions, those are pretty easy to understand. It turns out that these two errors are fundamentally different, and they can have drastically different results. So we give them different names. When the null is true, but we reject it, we call that the type 1 error. Okay. When the null is false and we fail to reject the false null, we call that type 2 error. Okay, and these are fundamentally different errors. Okay, we don't like any kind of error, but these two are fundamentally different. Okay, so let me give you two kind of practical ways of thinking about this. Okay, because you know, if you're like most people, when you're looking at this table for the first time, it does not really seem very user friendly, right? So let's go over here, and I'm going to use two examples. I've got an example from the legal system, and I've got an example from the medical system. Okay, so we've got a legal example, medical example. I think that should be, at least one of those should be interesting to you. Okay, so let's draw out the table here. Whoops, what was that? Never seen it do that before. Let's draw out our same table here. So we have our 2x2 grid. We have truth up here, and we have decision over here. Okay, so we can fail to reject the null, or we can reject the null in favor of the alternative, right? So in reality, the null can be true, or the alternative can be true. I mean, just practically speaking here, I guess you could probably come up with some strange pathological example, counterexample, but typically this is how it's going to work, right? Okay, so let's think about the legal system for a little bit. Okay, so let's say you are on the jury, and you are, so you're participating and you're listening to arguments, and so what's going to happen at the end of the jury? And so we're not going to think about the hung jury case. That is a possibility, but it just makes things too complicated at this point. So basically, you're either going to reject or fail to reject. What? Well, the null hypothesis, right? So what is the null when it comes to somebody's guilt status? Is the null that the person is guilty, or the null is it that the person's innocent? Anybody out there studying law, or maybe watch a lot of Law and Order shows, stuff like that? How does the saying go? Are they guilty until proven innocent, or are they I'm sorry, are they are they guilty until proven guilty, or are they innocent until proven guilty? Do we assume that they're innocent, or do we assume that they're guilty? Well, we assume that the person's innocent, right? Yeah, you know what I'm talking about, innocent until proven guilty. So the null is that the person's innocent. Okay, so the trial isn't about establishing somebody's innocent. Okay, they're innocent. During during the trial, right, up until the end of the trial. The trial is about trying to prove they're guilty. Okay, so it's innocent as the null hypothesis. Okay, so let's say you're there, you're in the jury, you go through the trial, and at the end, they fail to reject the innocence. Okay, so you find the defendant not guilty, right? Well, if the null is true, if they're truly innocent, then you've made the correct decision, and that's good, right? If you fail to reject the null, but they're actually guilty, then you've made an error. right? And what is that error? That's guilty goes free, right? So the person is guilty, but you did not find them guilty, right? So that's guilty goes free, and that's the type 2 error. Okay, so they're guilty, but they got off. Okay, now if you reject their innocence, but they're actually innocent, then you've made an error, right? This is the type 1 error. Okay, and this is where you punish the innocent. Does that make sense? So guilty goes free, punishing the innocent. I think you can tell those are fundamentally different. Now, neither one is good. We want to avoid both, but they're not the same kind of error, right? So that's why these two errors have different names. Okay, and then finally, if you reject their innocence and they're guilty, so if they're actually guilty and you find them guilty, then the system worked and that's a correct decision. Does this make sense? Okay, so that's one way of thinking about it. Punishing the innocent is a type 1 error, and then a type 2 error would be like letting the guilty go free. Okay, so now we don't want to do either, we don't want to make either of these errors, but I've got some bad news for you. How do you reduce the probability of making a type 1 error? Okay, so if you want to reduce the probability of a type 1 error, typically you're going to increase the probability of a type 2 error and vice versa. So if you want to reduce the probability of a type 2 error, then you have to increase the probability of a type 1 error. So these two errors, not only are they different, but they're kind of at odds with each other. Okay, so if you want to reduce one, then you actually typically end up increasing the other. What am I talking about? Well, well, I want to get your opinion on this. Which do you think is worse? You think punishing innocent people is worse, or do you think letting guilty goes free is worse? Armand is saying a type 1 is worse. So yeah, it looks like most of you guys are saying type 1, but maybe it's type 2, right? And you can think of cases, I'm thinking like, especially in times of societal instability, right? You might just, just to kind of get law and order back, established, you might have to, really, go hard on people, right? And maybe even end up punishing some innocent people. But typically, I think when society is functioning pretty well, I think most people would say the type 1 is worse, right? Does that make sense? So, but you can think that type 2 is worse. I'm not. I think you can make that argument, but in my experience, most students will say the type 1 is worse, and I would too. It's pretty terrible to punish the innocent. So yeah. So I would say the type 1 is worse. So if that one's worse, how would we make that less common? Well, if you want to stop punishing innocent people, what do? You make it harder to convict. At least that's one way of doing it, right? So if you make it harder to convict, what happens? Well, you start getting more guilty people being let off, right? I mean, if you make it harder to convict, then there's probably going to be some more people that are guilty that are going to go free. Does that make sense? Okay, so it's not always like a 1-for-1 zero sum kind of thing, but there is that sort of tendency, right? So that's just something to keep in mind. Okay, if we reduce the probability of type 1, then we actually increase the probability of type 2. So it's a little bit depressing how that works. Okay, so that's the legal way of thinking about it, and I really like that way of thinking about it. But there's another way, and that is with the medical system. Okay, so I like to give you guys both of these because it's just fun to talk about, and I think it'll probably stick in your minds a little bit better. So here's the scenario we want to think about. Okay, so the scenario is you are a fundamentally healthy person and you've never had cancer in the past and you have no symptoms of cancer. Okay, and you're going into your physical because it's your annual physical. You're not sick at all. And while you're there, your doctor says, okay, well, every few years we like to screen people for cancer. Okay. What is the null hypothesis about your status with cancer? is the expected kind of status quo that you have cancer or that you don't have cancer. Okay, so going into the test, right? So you're gonna have a medical test. What do you assume about your cancer status going into the medical test? Is the null that you are healthy or that you are ill? Do you assume you have cancer, or is the assumption that you don't have cancer? Yeah, you assume that you're healthy, right? So the assumption is no cancer. Okay, now this would be different, of course, if somebody had a history of cancer, or maybe if they had very obvious um, symptoms of a cancer, something like that. But the way I've set it up, the null is no cancer. The alternative is cancer. Okay, great. So let's set up our table. Okay, so I'm just going to do it over here so I don't have to write as much. Okay. Alrighty. So it's the same table. And so now we're thinking about this as a medical test, right? Probably by now in life you've had at least a medical test or two. If you haven't, eventually you probably will. Just kind of goes with the territory of growing up and getting older. Um, so if you had a medical test, you know what I'm talking about here. So the null is that you don't have cancer. So the test comes back and the test says, okay, fail to reject the null. So the test does not reject your health, right? And if you're healthy, then it's a correct decision, right? So it says it's negative, right? You're negative for cancer and it got it right. So it's a true negative. But what if it rejects your health, but in reality, I'm sorry, if it fails to reject your health and you're sick, then that's an error, right? And we've already said that that's the type 2 error. And what are they saying? Well, it's failing to reject the health, right? So it's a negative result, but in reality, you're actually sick, right? So we call this the false negative test result. Okay, and if I'm sure I bet some of you work like at a clinic or at a hospital, and you're probably already familiar with this term, right? It's a false negative test result. Okay, so it's negative. It says it's negative, but you're actually sick, right? So it's false negative. So the type 2 error is like a false negative. What if it says you're sick, right? It rejects your health, but you're actually healthy. Okay, that's the type 1 error. Okay, and so it's false. And if they're rejecting your health, they're saying you're positive for cancer, right? So that's a false positive. So the type 1 in the context of medical testing is a false positive. Okay, so in the context of the legal system, that's punishing the innocent. In the context of the medical system, it's a false positive. Okay, all right. So if you reject somebody's health and they're actually sick, then that, I mean, it's not good for the person, but at least the test got it right. Okay, so let's think about where you want to be in this grid. Okay, so the best place to be is here, right? I mean, this is like where you really want to be. You're healthy and you know it, right? Um, what is worse, the false positive or the false negative? Which would you rather have if you, okay, let me be clear on the question. The question is, what is worse, a false positive or a false negative? What's your immediate kind of intuition there? Yeah, great. You guys are all right. The false negative is worse because it says you're healthy, but you're actually sick, right? So you're going to delay treatment, right? You're just going to think, oh, those symptoms I'm having, it's not serious. It's something else, right? So this is actually the worst case, right? So with the legal system, you guys were all mostly saying the type 1 error is worse, but in medicine, it's common that the type 2 error is worse. Okay, so it depends on the consequence, right? It depends on the context and the consequences of these errors, right? So that's why we want to understand all the ways that the hypothesis test can go wrong, right? So this is actually the worst of all four to be in, right? Um, then where else would could you land? I think this would be like the second best. That's the false positive. So you go in, you get tested, and they say you have the disease, and so you're scared, right? And and it might create some psychological discomfort for you. But in the end, you go back, you get tested again, and then they say, oh, it's just a false positive, right? Okay. Now, I don't want to minimize the consequences of a type 1 error, of a false positive. I had a buddy who totally, his wife had some false positive test result. They ended up quitting their careers and moving to a different country. Anyway, it was a big mess for them. But typically for most people, the false positive is not as bad as a uh, false negative. Okay, and then probably the third best place to be would be down there. You're sick, but at least you know. Okay, so that's probably more time than we should spend on the type 1 and type 2 error, but it's such a neat idea and I like talking about it. So there you go. There's two solid ways of thinking about type 1 and type 2 errors. Okay. All right. So there's more there's some more definitions that we could go through and some terminology, and that's all great. But before we do that, I want to jump into an example. Okay, so I want to look at another study that was done. We have about 25 minutes here, so I think we have enough time to read this study and to get a little more practice with our applet, and then that'll put us in a nice place for Tuesday. We can spend about 30 minutes finishing up this stuff on Tuesday and still have a little time to review. Okay, so are there any questions about type 1, type 2 errors, or anything that we've talked about at all? Okay, so here's what I'm going to do. I'm going to pull up a video. There's actually a video on YouTube that we're going to watch to help us understand this study that was done. It's a really cool study. They were looking at babies and ethics of all things. Okay, so ethics, right and wrong. There's lots of ways of saying it, but so basically, by the time you're 18, right? By the time you're an adult, you more or less know what's right and wrong, at least in really basic cases, right? Okay, so there are some people who are you may not have developed that moral sense by the time they're 18, but the vast majority of normal people are going to know basic right and wrong. I think everyone would agree with that. Okay. Um, so at 18, that's pretty common to know right and wrong. But what about when somebody is a newborn? There's a domain of developmental. So I mean, does a baby who's 1 week old know right from wrong? Probably not, right? So maybe they do, but probably not, right? So at some point between birth and 18, you get more or less a pretty well developed sense of right and wrong, of ethics, right? Okay, there might be some scenarios that confuse you and you're not so sure about, but on basic issues you're solid, right? So these people are trying to figure out when that happens. Okay, so this group, these are developmental psychologists, and they work at Yale, and they published a paper about a study that they did with 6-month-old babies. Okay, and their conclusion is that even at 6 months old, babies can tell right from wrong. Okay, at least in some basic cases. Okay, so what we're going to do is we're going to watch this video, and then we're going to use it as a way of testing hypotheses. Okay, so we're going to take all that we've been talking about and put it back into like a full hypothesis test. Okay, and I think you'll find this interesting. Now, one thing here, for some reason, when I share videos, it gets kind of complicated. So I'm going to take just a minute here and make sure I'm sharing the screen correctly here. And I might need some help from somebody. I always seem to, okay, I'll share sound. There we go. I think I got it now. So Let me just let this run for about 2 seconds, and then I want you to tell me if you can hear the video, okay? So I'm just gonna run it for just a little bit, and you tell me if you can hear it.
Psychology called theory of mind, which involves.
Can you guys hear that? Good. All right. So just kick back and watch for a couple of minutes. You don't need to take notes from the video or anything. Just kind of listen to what they're doing and talking about. And it's cute. You see the little babies and just look at this experiment. It's really ingenious.
There's a domain of developmental psychology called theory of mind, which involves basically asking how do we develop an understanding of other minds? How do we come to understand other people's thoughts, their relationship between their thoughts and their behaviors?
If you both want to do different things, what could you do?
How we reason about other minds in the world.
Peekaboo!
We began addressing some of these questions with infants.
In this study, parents bring their 6-month-olds into the lab.
At the other side of a long table is a hill stage. A red circle guy with googly eyes tries to climb the hill. He sort of goes up the hill and then falls back down. He always fails at it. Then a blue square character, also with googly eyes, comes from the bottom of the hill and bumps him up to the top of the hill so that he's successful. On different trials, the climber tries again to get to the top of the hill, and then a yellow triangle character comes down from the top and bumps him to the bottom of the hill, so prevents him from getting his goal. Babies see this a number of times until they get nice and bored with it. So we stop and basically do a choice measure. The moms are asked to close their eyes. An experimenter who did not see which character was which brings over the two characters to the babies and just sees which character the baby touches first.
Which one do you want?
We found that, impressively actually, almost 100% of babies preferred the more positive character.
What do you want?
Okay.
They seem to have an attraction to helpful, pro-social individuals and also a real aversion to antisocial, unhelpful individuals.
Okay, so I hope you found that interesting, right? It's just you got these cute babies. You've got this interesting experiment they designed, and then it's an interesting question about human psychology and development, and it's a nice study for us to look at with our new hypothesis test framework. So let's think about the possibilities here. Oh, and then just a couple of other things. Did you hear that they had a double-blind experiment? Okay, it's called double-blind because they had the mothers, closing their eyes so they didn't, influence the choice the baby was making. And the person who brought it over wasn't the person who had selected the shape, right? So the person bringing it over and showing it to the baby didn't know which one was the helper or hinderer. So it was double blind. We'll talk more about that later. And if you were listening carefully, they talked about how they randomized the colors and the shapes. So it's not like it was always a yellow triangle that was the fiend, right? I mean, it was various colors and shapes. Okay, so let's think about the possibilities here. There were 16 children that they looked at, 16 infants. Let's see here. Okay, so sample size 16. And remember, we have p hat, which is the ratio of successes to sample size. So 14 chose the helper over the hinderer. Okay, so if we write that out as a decimal, that's almost 88% were choosing the hinderer. Sorry, the helper over the hinderer. Okay, so that's p hat. We're not really interested in those 16 babies. They're interested in all babies everywhere. Okay, so that might seem a little bit weird. I mean, how can you make a conclusion about all babies from 16, right? Well, they did publish this paper, and they basically proved that all babies, or I mean, if you look at the population of all babies, there is a preference for nice people to mean people. Okay, so what is P? P is the proportion of times the helper is selected, and it's not by the 16 babies, we know what that is, it's by all babies in the population. So what's the population here? Well, I don't remember exactly what sample they used, but let's assume that all of these babies were in the US, and they're probably close to Yale. So, they're probably babies there in the Eastern US, right? So it's still a huge population, right? And so, if we want to be a little bit more relaxed, we can just say it's just all babies, right? Okay, so if you were to take all babies and run them through this experiment, some proportion of them would choose the helper, and that's what P is. But we don't know what P is because you can't take all babies in and run this test on them, right? So we're going to use P hat to try to make an inference about P, okay? So there's two possibilities. We have the null and we have the alternative, okay? And you need to really practice this step here where you write out the hypotheses. You're going to have to do this on next week's exam. So they all begin the same way. You write H0, you write HA, and then you put a colon and another colon like that. Then you write out your parameter of interest. In this case, in chapter 2, it's always P. And the same for chapter 3 as well. We'll see after the first exam, P, okay? The population proportion. Okay, the null is always the hypothesis of equality, okay? So equal to something. And typically that's the standard, it's the accepted wisdom, or it's sort of the hypothesis of no effect, or nothing interesting, or nothing new, nothing that needing further research, right? The alternative is some kind of inequality. So it could be greater than, it could be less than, or it could be not equal, okay? Equal to what, okay? Or not equal to what? Well, what would be more interesting to you? That a 6-month-old does know right from wrong, or that they don't? What would be more interesting? That they do, or that they don't? That they do. Yeah, I mean, I agree. So that's the alternative, that babies can tell the difference between right and wrong. So the more boring kind of, hypothesis is the null, and so that's that they can't tell the difference. So if they can't tell the difference, then they would choose the helper half of the time, right? Roughly, right? So if they have no preference, then when they reach up to grab the shape, then they're going to choose the helper about half of the time. It's just by chance, right? Okay, so the null is that P is 50%, just like in our last study, right? With the head turning. What's the alternative? Well, if they do have some preference for helper, then P is going to be more than 50, right? So it's the same kind of test as we had before. Do all tests have this form? Not quite, not really. We'll see some other examples soon enough, but let's just do this example because it's fun, okay? All right, so then we need to think about something that's 50-50 in nature. Well, how about flipping coins? Yeah, so a flip of heads will be that they like the helper. Tails will be that they preferred the hinderer. So here's what we're gonna do. We're gonna go to our applet. You can do a coin if you want, but we need to speed things up a little bit. And we're gonna do a randomization, okay? So I need you to come over to this website. I put it up in the chat earlier, but I'll go ahead and put it in the chat again. I need you to click on that website, on that link, and head over to this website. Okay, so you click on that link and it'll take you here. And I need everybody to do this. Okay, so you're going to go here and you're going to go up to where it says one proportion over here. Okay, so click on that link that I sent you. It's also in the lecture notes, so you can click on it from the lecture notes. Let me just show you here. So somewhere here in the lecture notes, we have the link. Then you come over here to one proportion, and it's that coin flipper. Okay, so I need you to flip a coin 16 times. Okay, so let me show you how to do it. You put in 50-50 because we want a fair coin. Then you're going to go one here, and you're going to flip a coin. Then you're gonna flip a coin. You're gonna flip a coin 16 times. Why 16? Because that's the number that was in their sample in the paper. What we want to do is see how unlikely it is that we get 14 heads when we're doing a 50-50 process 16 times. So how many heads did I get here out of my 16? Do you see the results here? I got 1, 2, 3, 4 heads out of 16. Does everybody see that? So here's what I'm going to put in the chat. I'm going to put 4. I'm not going to put in tails or heads, or I get this many heads and this many tails. I'm just going to put in one number, and that's the number of heads I get out of my 16 flips. Does that make sense? If it doesn't make sense, I can explain it again. What do you guys think? Do you feel comfortable with that? Okay, so basically you go to this website, or if you have a coin, you can flip it 16 times real quick. Do it 16 times, right? So we have 16 total repetitions, and then I want you to tell me how many heads you get out of the 16. Okay, then you take that number, you put it in the chat, and we're going to generate a p-value. Okay, great. All right, so yeah, just keep them coming in the chat. The more the merrier. And if you want, just I'm happy to explain it again, but we are getting a little bit low on time, so. All right. So as you guys are working on your numbers there, I'm going to come over here to the lecture notes, and we're going to create our dot plot like we did earlier. So here's my dot. I got 4 out of 16. Killian came in at 9. Armand at 7. Noah was a 9. So notice I'm going to put a second dot. So Noah and Killian are both at 9, so that we're going to stack the dots. Brock is there at 5. Lindsay is at 9, so I'll stack that one on there. Julia also got a 9. Then we have a 10, and then we have a 6. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we got 9 participants. Surely a couple more people are going to come in with some dots here, huh? No? Well, it's okay if we don't have any more. We can still make it work, but it's always fun to have more. Nobody else? Okay, so what is it that we're comparing this to? Well, we're comparing it to their result. And what was their result? Their result, oh, you lost the question? Well, are you at the website with the coin flipping? So if you go to the website here, just click on the link that's above. Put the link back in here. So go to this link. Then that'll take you here. You go to one proportion. And since we're getting a little bit low on time, let me show you how to speed it up. Instead of 5 tosses, do 16 tosses. And it'll do it very quickly for you here. So you just do it one time for 16. Just if you want to super turbocharge the time here. So you see how I got 7 out of 16. So I'm going to come over here and I'm going to have a 7. It's a new result for me, so I'm just going to drop that extra dot in there. Okay. All right. So anyway, where are we at? In their paper, they got 14 out of 16. So I'm going to come over here. I'm going to put in a boundary at 14 over 16. And then my question is, how many of our randomizations, our simulations here, our randomly created simulations, did we get a result as extreme or more extreme? Don't worry about it. It's not a big deal. Thanks for trying, but yeah. How many out of our, let's see, how many dots do we have here? We have 10 dots. So in our 10 trials, how many were as extreme or more extreme than 14 out of 16? Somebody tell us. How many were as extreme or more extreme than? There was none, right? So 14, it's not a lot, but I think we are starting to get an idea of how likely it is that we would get a dot out here. I mean, we didn't even get any dots that were near there, right? All of our dots, they didn't extend past 10, right? So we call that the p-value. So our simulated class p-value is 0 out of 10 for a p-value of 0. Now that's as small as the p-value can get, right? So you might not be super convinced by that though, because it's only 10 rounds. So here's what we can do. Let's use a computer to knock this out of the park, right? So we're going to go back to the software now. And instead of doing it 10 times, we're going to do it 100 times or 1,000 times, however many times you want to do it. We can do it with software typically very quickly. So I'm going to build on what I have here. Every time I hit the button, I get a round of 16. Okay, and so we can just keep clicking it like this and getting 16 flips, you know, instantaneously, right? Okay, so 16 flips, 16 flips. Okay, and then so far I've done this 60 times. And remember what they got in their study. They got 16. So I'm going to come down here and I'm going to put in a boundary at 16. So again, what this tells us is if it's a truly 50-50 situation, right, an event that's a 50-50 event, and you do that 16 times, then this is giving us an idea of about how many heads we would expect to get. Okay, now if we want to look at it as a proportion, that's also good, right? So let's see, what was their proportion? It was, let's see here, so they got, what, 14? I'm not sure why it's not putting that in for me. So their proportion was 0.875. Let's see if that'll, there we go. Okay. So again, we've got nothing as extreme as what they got in their study. We got kind of close here. We've done this 60 times now. So let's do this a lot more, right? So if I do 40 more, now we've done 100 rounds of 16. And if I just keep doing that, okay, now we've done 220 times, and we did get it happening by chance. Okay, so in 220 rounds of 16 flips, it only happened one time, right? So that's actually quite unlikely, right, that we would get that. So that's our p-value. Now, because it's software, we can just keep going, right? So let's maybe do this 780 times, so we get an even 1,000 simulations. Okay, so we've done this 1,000 rounds, and it's only happened 5 times out of 1,000. So that should be pretty convincing. That's our p-value, 0.0050. Okay, so we have 5 out of 1,000, which is 0.0050. That's a small p-value. What do we do with a small p-value? We reject the null. So we are going to say, okay, the p-value is 0.0050. Alpha is 0.05. Since the p-value is less than alpha, we're going to reject the null. Okay, so the null is that babies can't tell the difference between right and wrong. So if we're rejecting that, what are we saying? 6-month babies have a preference for helpers over hinderers. Okay, now it might not be a perfect preference, but your typical 6-month-old baby, you know, on average can tell a difference there, at least in some very basic situations, right? So what do you think? I hope you find that to be an interesting study. And not only, so I hope that you find the psychology side of it interesting, right? The development of the mind to be interesting, but also I hope you find this testing methodology to be pretty ingenious, right? So that's what often happens with studies. You get some result, and you know, some people might think the result is significant. Others might say, no, that's not significant. And what the hypothesis test gives you is a way of determining if it's significant or not. And so if you read a lot of scientific research, you'll find, especially at least in quantitative fields, they use this hypothesis test a lot. Okay, I mean it's just kind of everywhere in various fields, and that's probably the reason you're taking this class, really, is to help you understand those kinds of papers, right? Because you know some of you guys are you know probably going into you know medical field or something similar to that, right? Maybe pharmacy school, or even if you're going, it's totally something different, but there's lots of great uses for the hypothesis test, and they are out there. It is used quite a bit. Okay, so let's look at the calendar here. We're out of time for today. We didn't finish all of chapter 2, but here's the thing. 2.4 is kind of like a summary section, so there's not really anything new in 2.4. I sometimes don't even talk about 2.4. Really, the last section with new stuff is 2.3, and we're almost done with 2.3. So here's my plan for Tuesday. We'll come in, we'll knock out 2.3 in about 30 or 45 minutes, and then we'll review for about half an hour on Tuesday, okay? Tomorrow, maybe later today, we'll see, I will post a video of a review session, a full hour-long review session I did for some other students, so you can watch that. So you'll have plenty of opportunities to practice, okay, and to review. And I'll also put in a packet of review problems for you tomorrow on Canvas, okay? So are there any questions as we break for the day? Anything I can help you with? Okay, so go ahead and get your exam scheduled. It should be available on their website. You don't want to wait until the last minute because sometimes they get full or there's some kind of error on the website or something, right? So anyway, have a good one, guys. Have a nice weekend, and I'll see you all on Tuesday, okay? Thanks so much.